Okay, today we're going to take a step forward and a step back in review with regard to the topic of the course, which is fluid properties, and what's normally referred to in the petroleum industry as the PVT behavior of fluids. And what's really meant by PVT, of course, that stands for pressure, volume, and temperature. But in reality, this fluid behavior that we're talking about when we refer to PVT represents kind of three categories of properties and in a sense a description of these fluids in three categories that are useful for engineering applications. And the first is, we usually refer to it as phase and volumetric behavior. That's typically what we call this more formally. And then there's a couple of extra things in addition to the phase and volumetric behavior. And I just want to review a little bit what we're talking about for the three categories of fluid behavior. And when it comes to the phase behavior, what we're talking about, of course, we have to define what are the phases. Well, for our systems, they would be gas, oil, and water. Aqueous phase, for example. And we'll find these phases, at least two of them, in all situations when we're producing gas and oil from a reservoir. You may only find gas and water, you may only find oil and water, but you might find gas, oil, and water all in the same reservoir. And of course, if you only find water, then we're probably going to be out of business soon if that's all you find. So generally we're going to have at least two of these, and we'll always have water in the system. I'm not going to talk at all this morning or in this course about solid phases or semi-solid phases that form or exist in petroleum systems, but they are part of fluid behavior. And well, they're not really fluids, but basically they don't flow. So it would be something like an asphaltene that precipitates out from an oil. It could be a wax that precipitates out of an oil. Perhaps hydrates might be considered a solid to some extent. But we're not going to talk about these solid phases. But we will be talking a lot about gas, oil, and water. And for the most part, both the book that is used in the course and the lectures during the semester will deal mostly with gas and oil, but I'm going to take a step aside this morning to talk a little bit about water in connection with gas and oil. And that is dedicated to chapter 9 in the book, but we're not really going to cover that in the course. But I will touch on how water, gas, and oil interact. So now when one talks about phase behavior, it's typically referring to the thermodynamics. So this is a word that you guys have had, thermodynamics. Sometimes thermodynamics would be referred to as phase equilibria, or chemical equilibria. You may have heard of it, referred to it in this way in your previous courses, chemical equilibria. These are three terms that refer to the formal definition of what phases exist, given a set of compounds that are mixed together, methane, ethane, CO2, H2O, and so forth. We'll talk about the compounds that we typically find in petroleum systems, review that again. But when you get this mixture of these different species together, which phases actually form, and how much of those phases and how much of those individual components partition into the phases that do form, that's really what's calculated or in a sense dictated by thermodynamics. That was laid out formally by people like J. Willard Gibbs, van der Waals, and the likes. So this is our field of thermodynamics, and so we're interested in which phases form. Are they saturated? Are they undersaturated? We're interested in the composition of each phase, which basically says how much of each component is in each phase, and the amount of each phase. So that's really what we're going to work our way into in some great detail during the course. So we'll talk more about that here, but let's just look at the volumetric behavior, because we've already spent some time on that in terms of gas. Basically, volumetric behavior is where you're looking for some function of the volume of the phase, of a particular phase, as a function of pressure and temperature, hence the term PVT, but also what I'll refer to as, this is basically our composition. And I'm going to use the term UI. It's not used in the book, but it's kind of a generic molar composition. It's the relative amount of methane, ethane, CO2, H2O, and so forth in a given phase. Okay? Now, for the phases that we know of, gas, we've got the term is YI that we use for mole fraction. For oil, we use the term XI for the mole fraction in oil phase. And if we have a water phase that we're going to deal with, then I'm going to use the term XWI. So basically, X of I means it's a liquid phase. In this case, it's oil. In this case, it's a liquid phase, but we give it the extra term W to designate that it's a water phase, and the YI simply means it's a gas phase. Okay? And of course, mole fractions are, in a sense, just defined as the moles in that particular phase over the total number of moles in that phase. So I'll just do generically the number of moles of component I in the phase over the total number of moles of that phase. So if it's a gas phase, then this would be defined as the moles of component I in the gas phase divided by the total number of moles in the gas phase. Of course, that would just be the sum of all of the moles for all of the components summed over I. Like that. So these are just definitions and nomenclature and terminology. But the volumetric behavior is basically interested in defining how the volume of a phase changes with pressure and temperature given a composition. Okay, and we have a few other terms that we've been using in talking about gas during the course. We have something that we call the molar volume, which is just the definition being the actual volume in cubic meters or cubic feet divided by the number of moles. A molar volume. We have defined in connection with gas, but there's a generic definition of another volumetric property, or it's really just a variable. This variable Z is defined as pressure times volume over nRT, which is of course the same as pressure times little v, the molar volume, divided by RT. It's just a definition, but that Z as a variable is commonly associated for most petroleum engineers with the gas phase, but we actually will use it with oil phase, and we can even use it with a water phase when we start solving these more complicated thermodynamic problems. We want kind of a generic terminology to do that solution to the general gas, oil, water phase equilibria calculation. So these are two terms that we've used for volumetric quantities. And the last one, which is really important for engineering applications, is the mass density, because the mass density, when multiplied by the acceleration due to gravity, is what causes pressure increase as you go down in a column of water, gas, oil, whatever you have. So the pressure is tightly coupled in a static column of fluid to the mass density, and that is a very important engineering quantity for really any engineering field, and it is the mass density. So that's defined as the mass over the volume, which we could write, I suppose, in terms of this generic Z factor. We could write it as pressure times the molecular weight over RTZ. That's how you would calculate it, knowing pressure and temperature and the Z factor. So this is mass density. Again, it's always used, for the most part in engineering, multiplied by the acceleration due to gravity. And that gives you a pressure, basically a pressure gradient with vertical depth. So those are some of the volumetric issues of behavior that we're looking at trying to calculate. We've already talked about some of those for gas. We haven't really talked at all about the thermodynamics of systems, component partitioning, phases, saturation phases, and so forth. Now, what are these extra things that don't really fall directly into these two categories? Well, the two properties that we also have to come up with to do engineering calculations, for sure, the one is viscosity, which has the symbol mu, and the other is interfacial tension between two phases, or it could be between a fluid phase and a solid phase, but in general we're going to talk about fluid phases, so we've got interfacial tension. Sometimes that's referred to as surface tension. The symbol for that is sigma. Often you'll see it referred to as IFT, interfacial tension, as a symbol, or not a symbol, but you'll see this often referred to it. But it may be called surface tension as well. And here you have to have two things to have an interface. So you have to have two, in this case we'll look at phases. So we'll have, for example, gas oil, gas water, oil water. So we would write them like that. So you have to say which two phases. There might be a solid phase, and would be written SG, solid phase between gas and a solid. But I'm not going to talk about solids today. I think we haven't referred to units. I'm not going to bother you too much with those, but because we'll get into those later. But for viscosity, basically the SI unit is Pascal times second, and the engineering SPE unit is centipoise. Poise is the guy who kind of, like, I guess, came up with the concept of viscosity or did something early on with viscosity, so he's honored. This Poisel, poise is, I think, related to a name. Centipoise, and there's an exact relation between Pascal seconds and centipoise that I'll just make a note of here for you. It's basically that you have 1 millipascal second, okay, which is an SI unit, is exactly equal to 1 centipoise. So 98% of the books and the literature you read in petroleum engineering uses centipoise. So if you want to think about centipoise, you don't want to learn a new term, just think in terms of millipascal seconds. I think IFT, interfacial tension, has units of Newton per meter, or in the units that we typically use for more petroleum engineering, it's usually referred to as dynes per centimeter. And I believe that this is correct. 1 millinewton per meter is exactly equal to 1 dynes per centimeter. I think that's correct. And when I say I think it's correct, it means that you probably need to check it in the Appendix A. Okay? Remember, I think I've told you my motto. I could be right, but I might be wrong. You know, it's kind of the way it is in real life. So it's best to check. But these are the extra properties that don't really fall directly into. I mean, they're kind of derivative properties of the traditional phase and volumetric properties. Are there any questions? Okay. So PVT refers to pressure, volume, temperature, but it really means we're talking about phase and volumetric behavior, plus plus. Phase being what kind of phase do we have, how many phases do we have, how much of each phase, and what are the compositions of the phase. The volumetric is, for a given phase, really what's its density, what's its mass density. That's what we're really interested in. Okay? And then we have the viscosity, which of course is important in practically any phenomena where you have flow. And if we don't have flow, we don't get paid, right? So we've got to flow the stuff from the reservoir up to some pipeline into some refinery or gas plant. So viscosity is everywhere. Density is pretty much everywhere. And certainly the properties, derivative properties, are sometimes important. Okay? So that's what you can tell your mom and dad, you know, what you're doing in this class on Thursdays and Fridays. It's kind of the overview of what we're doing, what we're talking about. Okay? Now, if we look now at phase and volumetric behavior in a more generic sense, what we have done is that we basically are going to use, we're going to have laboratory data that we'll talk about during the course, and then we're going to have models or equations that we can use to describe those laboratory data, or when we don't have laboratory data, to predict the properties from these equations. Okay? And to do these phase and volumetric predictions, we need what is referred to as equation of state. Okay? And we've already talked about the gas equation of state, which is pressure times volume is equal to the number of moles, the gas constant times absolute temperature. We've already talked in great detail about that equation of state. But that equation of state can only be applied, in reality, the way I've written it here, this is for ideal gases, okay, low pressure, very, very high temperature gases. And then we have a more generalized form of that deals with all gases. So we call this real gases. That would be also at high pressures, lower temperatures, but it's behaving like a gas, where we add this Z factor, and we'll tag on the G there, the gas Z factor, which came from us from 1941, I believe, January 1941, the Standing Cat's Z factor chart, which is a function of pressure, temperature, and composition. Remember, this ZG is a function of pressure, reduced pressure because of van der Waals corresponding states theory, reduced temperature, and in this case, since it's a gas, the gas composition. So we have a means to deal with gases. we haven't really talked much about oils and what we need in terms of coming up with the phase and volumetric behavior of oils alone. I will mention that for the gas equation of state here, it's limited only to describing the volumetric phase behavior. It generally is not used for phase equilibrium thermodynamics, okay? Because for this phase equilibrium thermodynamics, is the phase saturated? If so, with what oil? Well, this just doesn't describe oils, so it can't tell you anything about this oil that may be forming from the gas. So this is purely giving us volumetric properties. It's not giving us phase equilibrium properties, in other words, how the gas converts into a liquid or how the liquid converts into a gas, because this equation doesn't describe anything but gas phases. Okay? We're not going to talk too much, but I'll just give you a simple example of an equation of state for an oil. It's not something we really use, but that would be, for example, that the compressibility of the oil, which is defined as -1 over volume, the partial of volume with respect to pressure, and this would be at a constant temperature. So that derivative might be changing as a function of temperature, but basically this gives at least a pressure-volume relationship for an oil. And you might say that, well, for some oils, this is approximately constant. That would be a simplifying assumption, but it would be an equation of state. It would only apply to oils and what we call slightly compressible oils. That's generally not used. And that, again, would be just used for volumetric applications. But what we really want and what we really need to talk about phase equilibria, okay, how a gas miraculously transforms into an oil, or an oil transforms into a gas, okay, we need a general equation of state that works for both gases and oils. That's what we need. And Chapter 4 is dedicated to talking about that kind of equation of state. Okay? One equation that will handle both gas-like behavior, oil-like behavior, and the behavior of the fluid system when you don't know if it's a gas or an oil. Okay? And there's a big chunk of pressure, temperature, space where you don't really know if it's gas or an oil. And this equation of state, this general equation of state, will be able to describe any fluid at any of these state conditions. And the general equation of state that we use is typically a cubic equation of state. It doesn't have to be cubic, but this is basically the simplest form of a generalized equation of state that has been proposed and is being used actively by the industry. There are other more complicated equations of state that do the same job, but they're not much used in the petroleum industry. Almost exclusively from reservoir, production, drilling, processing, pipeline transportation are using these same cubic equations of state. Okay? To do the work. And I'll just give you the simple form of this cubic equation of state. It's written something like this: the same gas constant, same absolute temperature, same molar volume, and there's a constant B. Okay? And then there's a second term. This is describing the pressure given the volume and temperature. There's a second term with another constant A, and then you've got a denominator here, and depending who your name is, and there's like three three names that are now famous for three cubic equations of state that are famous, okay? Depending on who your name is, this denominator of the second term will look a little bit different. But all of them have a v squared term in them, okay? All of them have a v squared term. Now, before I give you those v squared terms for the three famous sets of people, I'm just going to make a comment about what this equation of state is trying to do. And it was originally proposed by van der Waals. I think we already talked about him in another connection. He did lots of cool stuff in the 1870s. The theory of corresponding states we already talked about. But he introduced this equation of state, I believe, as part of his dissertation thesis for his PhD around 1870 something, 60. And what he was trying to do was describe the molecules and the fact that he either knew or proposed intuitively or had experimental evidence for the fact that if you put a bunch of molecules too close together, okay? If you keep crunching all these, you take 100 molecules, you take us, okay? And we start closing the walls in on us. The ceiling comes down, okay? What's going to happen to the pressure in this room? The social, the psychological pressure in this room. What's going to happen to that? It's going to go sky high, because I can guarantee you, I am, what do you call it when you're afraid of closed spaces? My pressure is going to go real high. Probably some of you as well. Okay, you get the molecules closer and closer together, and they want to do only one thing. They want to get further and further away from each other. Okay, so these are in a sense, the repulsive forces are being described by this term. And you can kind of see it, because as the volume of this room becomes the physical volume of us folks here, meaning that we have no space between us, at that point the pressure is going to go infinite, right? I mean, we're all going to be screaming and yelling and going crazy. And that's basically the same kind of thing that happens with molecules, except they don't do it because of emotional or psychological state. They just do it because that's nature. And this first term is describing the repulsive forces between molecules, air molecules, water molecules in the air, etc. And the second term are the attractive terms. That means okay, maybe we don't know each other that well, but let's say that we're a family, or we're a football team, or we're the TV program Friends, okay? If you send us away from each other, let's just stick with family, because in general we're in good terms with each other. If we all go our own ways, we go far away, each one a different country, a different corner of the world, we're going to miss each other, right? And there's going to be an inherent force to try to bring us back together. So if the volume between us gets too large, we're going to have a natural tendency to want to come back together again. And those are the attractive forces. Okay? And this term, this second term, A over some V squared, is describing those forces. And the composite of this, because nature is such that we're now in a room of so many square meters, or cubic meters, and we're so many cubic meters in size, so it's about the right size. Nobody's, claustrophobic and wanting to run out of the room, at least because of the claustrophobia. Okay, maybe for other reasons. But the balance for this fixed volume is some balance between these two. Okay? And I like to describe it a little bit like it's kind of marriage. Of course, maybe most of you haven't been married yet. Or it could be like your brothers and sisters in a small house. There's this balance of, in a sense, the repulsive and attractive forces. So nature is always balancing out the equilibrium of these components, okay? And Mother Nature takes care of it automatically. You know, the components know where they need to be at a most happy state. And that is what we call chemical equilibrium. Okay? Nature's always trying to bring all of the molecules into equilibrium so that we're all happy troopers. Okay? And that's what this chemical equilibrium and thermodynamics is trying to do with us. And we have this equation to do that. So I'm going to just mention what the three famous people that have these three different terms. The one was the original van der Waals. I'll just shorten it by that. Again, this is all discussed in Chapter 4 in great detail. I'm not going to tell you more than you can go read. The van der Waals term, denominator of the attractive term, is exactly equal to v squared. Simple, sweet, and pretty accurate. Okay? And then around 1949, there was a couple of guys, Redlich and Kwong, okay? And today's version, they throw on this Italian guy up front, Soave, like the wine. Soave, Redlich, Kwong. But the actual form of the equation came in 1949 from Redlich and Kwong. And they, let's say, improved things over the van der Waals by using this term. I was going to write it with v squared, but you'll see the v squared come out of it. V times v plus the same term b as is in this repulsive term, right? Okay. Do we know the value of b for this room, for this group of people? We could certainly measure it, right? It is the sum of our body volumes. So we just each one jump into the bathtub, we measure the increase in the height of the water. Okay? It'd be kind of a strange experiment, but we could calculate very accurately the B value for this room. That's when we go absolutely bananas, crazy. I mean, pressure goes to infinity. Okay? So this B has actually got a physical meaning to it. It's the size of the molecules. Okay? It's the size of the molecules per mole. So he throws that B term, though they threw the B term, but you see it's got V squared plus BV. And then the last one, they came in around the early 1970s, late 1970s, 1977, I think. Just the year before I came to Norway, not that that's anything special. Pang and Robinson. I believe Pang was a graduate student of Dr. Robinson, who I believe was one of the Donald Katz University of Michigan folks. I think Robinson was in that group, and he went up to Canada, university there, and became a very famous professor, and he's most famous for this Pang-Robinson equation of state. And he also started a company called D.B. Robinson, which was later bought by Schlumberger, who I'm sure you've heard of. And their equation, they started with the same as the Redlich-Kwong, and then they added another term, which was B times V minus B, okay? And that's that term for the Pang-Robinson. So it's the same as this Redlich-Kwong, but then they add on another term. For reasons we're not going to go into here. Now you can see, or maybe you can't see, but this equation of state is supposed to work for both gases and oils, okay? And you can kind of see that if we just evaluate a little bit the terms here. Well, as the volume gets very small, the pressure gets very large. That's behaving like a liquid. It's behaving like a liquid. So that you can see that that second term becomes unimportant if the V approaches the B. You basically get this pressure going to infinity just from the first term. For the ideal gas law, you basically have V going to infinity as pressure goes to 0. That's kind of like the limiting case of an ideal gas at the extreme. Well, what happens as volume gets larger and larger and larger? Well, it's the denominator of the second term that will always dominate because it's got a V squared, right? So you can just eventually at some point when the volume gets large enough, that first term becomes negligible, becomes like an epsilon. So, and if we look at any of these terms as I'm sorry, the second term disappears because it's the volume is getting large faster for that term, so the second term disappears, and we're left with the first term. Okay, we're left with the first term. But as volume gets very large, it's getting much bigger than B, so we can ignore the B. And so as volume gets large and goes to infinity, we basically end up with V pressure is equal to RT over V because the B is small. And that is the ideal gas law. Okay. Any questions about this?
Yeah, maybe one question. You said the B parameter means like size of molecules to mole, right? This equation.
In a sense, yeah. That's kind of a physical interpretation of B.
Right, what's called A?
A is, it doesn't have such a simple physical interpretation. That I know of, or that I've thought of. Okay. Well, you guys should have some question. I mean, there's obviously, you know, if I say, well, I want you to use this equation to calculate the pressure, volume, temperature behavior of methane, or let's say water, you know, let's take water because it's something we grow up, you know, every morning. You know, I just watch the water boil over here, you know, so I can get my coffee. So if I tell you I want you to use this equation for water, and I want you to describe the water in my cup, which is just boiling, and the steam that was coming off the machine over there, how would we do that? How would we go about doing that? Would we Google the A and B for H2O or something? I mean, you have to have A and B. You guys have to be curious about, you know, where do I come up with the A and B, right? So we need A and B to use this equation. Okay.
Would be a fixed number for each substance?
Could you speak up just a little bit?
Yeah, would be a fixed substance for each.
That's right. B would be a fixed number as well as A for each substance. So H2O is going to have its special A and its special B. That's right. exactly right. And you know, there are books that have A and B. They're not, yeah, but there are not very many of them around, and that's because both van der Waals to begin with, and these other guys kind of copied what van der Waals did. Van der Waals gave a method to come up with a good estimate for A and B for any given component. Nice guy. Today, if we would have been asked to do something like this for steam, you would have gone to this, you know, Google the steam properties. You would have seen pressure, volume, and temperature in tables, right? You could have put in, you know, there's probably 10,000 numbers in these tables. Load them all into Excel. You've got a simple equation, you know, with temperature and volume, many different combinations of temperature and volume for steam and liquid water and so forth and so on. And you could just simply have two cells in your Excel sheet that's A and B, and you do this like best fit of all the steam data, the steam table data that you have on the internet. That would be one way to go about coming up with A and B today. Because we have, at least for water, we have a huge tabulation of measured pressure, volume, and temperature for water as a liquid and as a vapor, gas. But in 1870, we didn't have Excel. We might have had the tables. I'm not sure about that. Probably did. But you certainly didn't have Excel. You didn't even have calculators. And, you know, van der Waals was limited. He was a smart guy, but, you know, he didn't want to become a slave to his own equation, computing with the, you know, some kind of computing machine to do a best fit to the measured water properties. So van der Waals did things different, and it's kind of unfortunate because it's a symptom of our overload of information and data today. Because today, the guy who came up with this, if they hadn't come up with it, or the girl, they would immediately think, I've got all this data, I'll go fit the A and B to the data. And that would be a natural thought because you have regression packages within Excel. It's all straightforward. But instead, what van der Waals made the observation that every compound they knew of back in the 1870s had one characteristic pressure, volume, temperature behavior. Okay? And what he knew is that at some special temperature, which I'll just call T star for now. The measured data that was available, pressure versus volume, will always be monotonically, you know, decreasing as you go to larger volumes. But at one particular temperature, the pressure volume behavior looks something like this. And what's special about this behavior is that right at this point here, the derivative of this pressure volume data, the derivative here is 0. Okay? And because it's always a monotonic pressure-volume relationship for any fluid, that means it doesn't go up after reaching this kind of flat point. It doesn't go up again. It also means that the second derivative of pressure with respect to volume was 0. And it was the same for methane, water, nitrogen, CO2, whatever they had compiled data for. And of course, what's the special temperature? We come back to that. But the point was that at this particular temperature and at this particular pressure, which we'll just say P star as well, and at this particular volume, V star, we had these two equations. two equations and two unknowns. Okay? And that you could solve for analytically, directly. If we knew P star and T star, then we could find those A and B straight away. So by solving these two equations, and by noting that the T star was in fact equal to this critical temperature we've talked about before, and that the P star was the critical pressure, you can then, solving these two equations, you can come up with an expression for A, which is R squared TC squared over PC, and B is R TC over PC. Now there's a numerical constant in front of this first term here, which I don't think it was van der Waals, I'm not sure who it was, gave this numerical constant a fancy Greek letter. This is a number. It's the same for all compounds, water, methane, whatever. There's also a number here. Okay, it's a different number. It's a number 2 and number 1. Okay. And that number is a little bit different for the van der Waals cubic equation, the Redlich-Kwong cubic equation, and the Peng-Robinson cubic equation. It's name specific. Okay? And the number is always around 0.4 for A, omega A, and it's always around 0.1 for omega B. Okay? I think for the van der Waals, just to give you those numbers, I think this is 27 over 64. I should probably check this. I think this is 1/8. You can check that in chapter 4, but I think those are the numbers, and they're approximately 0.4 and 0.1. And so he gave us a simple way. All we have to know is critical pressure and critical temperature, and in any chemical handbook on the internet you can find critical pressure and critical temperature. You can go straight and get the A and B for that compound. Okay? Okay, any questions before we take a break?
Is there any recommendations? What's equation of state we should use, like for van der Waals or for Peng-Robinson, or they have kind of similar result?
Yeah, in a sense, the industry only uses these two today. Okay, and because the process industry started using cubic equation of states earlier than did the reservoir petroleum engineering industry. Okay, the reservoir petroleum engineering industry started around 1980 using them. The process industry started around 1970. Okay, and because of that, the process industry has kind of a relationship, a history, at least the ones who are retiring now, with the SRK equation of state. And the folks, well, it was Peng and Robinson, and they were in the upstream and more of the upstream. So they published in the Society of Petroleum Engineers journal first. It was Katz and Firzabadi who published kind of the Peng-Robinson equation of state. In our literature, reservoir production petroleum engineering first. So most of us kind of got used to using the Peng-Robinson equation of state. In reality, my standing bet is that if you have an SRK equation of state that you say is best, I have to have the SRK, it has to be then I'll make you a bet of $1,000 that I can construct a Peng-Robinson equation of state that gives essentially the same behavior for all the mixtures of interest as yours. Okay? It doesn't mean that there's not a reason to have a favorite or a familiar. You work with what's familiar. But in reality, it's like two sets of units. You generally can get the same quality of description of data with either one of them. So, okay, so we'll take a break.